Signal and noise in measurement systems. This is film number 1, which is the introduction to noise. And what is noise? Well, noise is when we have signal that is mixed with the original signal and it's undesired. So we really don't want noise, definitely. And but we have other problems with the signal as well. So if you have this as the original signal, of course when I send this from a sender to a receiver, this is what I would like to receive as well. But sometimes I have problems with the signal, and in most cases actually I have different degrees of noise. Noise is when we have some extra energy in addition to the original signal that we once had. And then another problem could be damping. You see this here is far lower than the first signal, so we have lost energy. And here actually we had some extra energy. So extra energy is noise, loss of energy is damping, and then we have something called dispersion. And dispersion is when we have the same amount of energy at the receiving side, but the energy has been spread out in time-wise, in the time plane. So I have this square pulse that I sent, and this is what I received here. So it has been spread out time-wise. And the problem here is if I have two neighboring signals, like that pulse and that pulse there, and together they melt into one signal where you can't clearly see which one is a logical on and which one is a logical off. So they melt and mix with each other. But this chapter here, this presentation will be mostly about noise. But we should be aware that most signals suffer from all three of these elements: noise, damping, and dispersion. Noise is, as said earlier, undesired. We really don't want noise into our system, of course, and it appears in all electronic circuits. It's impossible to get rid of noise. However, we have tools so we can live with the noise that we have and even remove the noise from our signal at receiving side again. One of the tools, digital signals, they are less prone to noise, so that's why you will hear better from a digital source. The digital source will seem to be more free from noise than an analog source. In physics, it's an undesired disturbance, so it's a disturbance and it's undesired. It's frequency dependent, which means that you have low frequency noise and high frequency noise. In audio terms, you would say that you have bass noise and treble noise. Bassdiskant på norsk. And it comes from human or natural sources. So it may come from a source that we have generated as well, or it just comes from, for example, cosmic disturbances. Deterministic noise is a noise where you can predict the future value. So you can determine the noise, that's why it's called deterministic. And it's, for example, the hum from power supplies. And here is an example of how this hum works. If we copy this page here into the here, you can hear the hum like here. I guess you have all heard that before. And then we have random noise, which is it's not possible to determine. The noise that we just heard was a 50 Hertz noise, so you can actually filter out the 50 Hertz and get rid of most of the noise. But random noise is much easier to remove, which gives the answer to the question down here. But anyways, random noise, let's give an example for random noise. So if I take this page here and I guess you heard that before. It's a mix of all possible frequencies, and it's not easy to predict how the future value should be. But the first noise here that we heard, the hum, was a 50 Hz noise, so I can actually have an equation in the time plane for it. Just sine and 50. So that is easier to understand than this kind of noise. However, we can study the statistical representations of the noise. So if we analyze our noise, we need to observe with small time steps what is the noise. We need to study the noise with small time steps like this. We need to study it for a large amount of time, and then we need to have a noise that is stationary, that is not changing, so it becomes more and then less 15 minutes later and so on. So if we study the noise thoroughly, then we can make statistical representations of the noise, and then we can learn what to do with noise. So we can, for example, have the probability density function, giving what kind of mean amplitude we have and what is the standard deviation from the amplitude of the noise. For example, here I have one noise here. If this is voltage and this is time, if my voltage, noise is about here, you see the mean voltage is about there. And if I have a second noise with the same mean but much larger, that will mean that it has a larger standard deviation to it. And then we can have something called the power spectral density function here. And that is when we have we learn about the noise, what kind of frequencies are involved, like bass and treble, basso discount. So by doing those analysis, we can understand our noise and understand what we have to do with the noise as well. Another example of the different frequencies of noise is here, where you have white noise, pink noise, blue noise, and gray noise, like that. And they are called the colors of noise. Of course, they are not white, pink, blue, and gray. You can't see the noise, but you can hear it, and you can measure it. But the thing about white light is that it has even amounts of all wavelengths in the light, which means that it has even amounts of all frequencies. And so does white noise. It has even amounts of all frequency components. A pink light will have an overrepresentation of long wavelengths, which means low frequencies, and so does pink noise, overrepresentation of low frequencies, bass. Blue noise has an overrepresentation of high frequencies, which is treble, and then gray, bass, treble, and very little midtone. Here are examples of self-generated random noise, and I will not talk too much about them. Just mention that thermal noise has, by nature, increases when the temperature of the device increases. And it has to do with the random movements of charge carriers, as it said here, which basically, if you have a conductor like this, and you know that when you have current going through it, the electron current goes from minus to plus. So you have electrons moving here, and they all move from left to right. Well, that's just part of the truth. The real truth is that the electrons, they on average move from right to left in this figure here. Real electrons sometimes move like that, some move like that. Then you have some that move really fast, and even some that move the wrong way around, but on average they move in that direction. So if I have a cross section here of the wire and I try to count the amount of electrons that go through there, well, it would be like that. But if I study it closer, I zoom in on the graph, I would see that you have random movements like that, and that's the thermal noise, because electrons move more and faster when the temperature goes up.